So associativity, first up, top of the lineup. So remember, associativity really has to do with how much searching we're doing. So in a fully associative cache, which you can see over here on the left, what we'll be doing is associated with each piece of data in the cache is of course a tag. That's true in all cache architectures. But we have a separate comparator for each tag. And what that means is an incoming address here could be compared against all the tags in parallel. We're going to search every possible cache location to see if it might contain the address. And that's great because that, as we'll discover in a moment, that does a great job of solving potential collisions. If there's multiple addresses that might map into the same location in the cache as over here in a direct map cache, they might collide and sort of keep playing bumper cars with each other, kicking the other guy out. Over here, there's no such there's no game of bumper cars. Any location can live anywhere, and so the fully associative cache always has the n most recently used items, okay? Whereas the other caches don't have that. So in a sense, the fully associative caches are gold standard for how well a cache can perform. Okay, it turns out to be very expensive. Only a small fraction, a little less than half usually, of the circuitry associated with a fully associative cache is actually devoted to storing the data that we want. So it's an expensive thing. It's also pretty power hungry because there's a lot of circuitry running in parallel here. The other end of the spectrum that we explored last time was a direct mapped cache in which we use the low order bits of the address to select a particular location in this. So the cache itself actually has a lot of memory associated. Just think of it as a big static RAM that has lots of locations, maybe 1,000 or 16,000 or something. That's sort of the sizes of the caches that you have in your machine. That each hold a data word and a tag, but we're not going to search all of them. In fact, we're going to use the low order bits of the address to select a particular one to look at, and if that happens to be holding the address that we want, we're golden, and if not, it's a miss. We're not going to look anywhere else in the cache. So what we have here now is a very compact system in terms of hardware. It uses these efficient static memory structures quite well, and it has one comparator. The disadvantage is, of course, we're only looking in one place, which is, as we'll see in a moment, gets into trouble. Do people remember why we use the lower order bits of the address to determine where to look in the cache? Yes? Right, so our locality of reference is really saying it's the low order bits of the address that are changing. Right, the notion is, like as you were pointing out, the example of a program counter, as it goes through a loop, and when we look at the addresses of the instruction, those addresses differ in their low order bits. And so what we want to do, for example, is hopefully all the instructions of a loop would fit into a cache. So by using the low order bits to determine where to look in the cache, what we're doing is we're taking things that are most likely to be referenced in short periods of time and making sure that our mapping function between the address and the cache location spreads those out into different cache locations. Okay, so that's why we use the low order bits. And then, of course, what we're doing is we store the high order bits of the address, okay, of a memory location in the tag, and we compare that with what the high order bits of what's being asked for. So a combination of what line we're looking in and then the tag comparison will basically do the address match for us, but we're only checking in one place. Okay, so we're checking everywhere or we're checking only once. And I hope everybody can sort of understand that there's a middle ground here, which is maybe you could check in 3 or 4 places. And so we're going to sort of explore that middle ground now. So first, let me just start off by pointing out the problem with direct map caches. Here what we have is a little program loop. It's running at word address 1024, so you can see a little 3-instruction loop that just repeats again and again and again. It's going off and accessing some amount of data that's stored, in this case, at word 37. And you can see that these addresses, when we figure out where they live in the cache, live in different parts of the cache. So just to remind ourselves once again, how would I take a word address and decide where it is in the cache? Well, we have a 1024 location cache. So what I'm asking is, I got a 32-bit address from the beta. Since we're dealing in word addresses, I'm going to leave off the bottom 2 bits. Okay, what address bits do we use to access the direct map cache? The low order bits. And how many of them? Because we have a 1024 location cache. 1024 is 2 to the 10th. You know, by the time, I'm sorry? Yes, the 10, so these 10 bits right here, okay, are the index into the cache. So what we really want to do is to take the word address mod 1024, right? And so that's why address 1024 maps to cache line 0, and address 1025 maps to cache line 1. So this is more than academic. We're going to spend some time, certainly you're going to be responsible for figuring out, if I do run this little loop, how well will it work on a particular type of cache. What you need to do is to turn the addresses the CPU generates into figuring out which cache lines will be accessed. So you have to understand this address mapping to cache line, or this address to cache line mapping, in enough detail to be able to figure out what cache line an access is going to. So that's what we've done here. And they all come to different cache lines, so they could all potentially be hits. However, if I change the data location, if I somehow, you've edited the program, you've added a couple more arrays that have nothing to do with this loop, but you've moved where what used to be at 37 is now at location 2048. Okay, you didn't think you changed anything, but the addresses of where data were being stored changed, and now you can see that your program will actually run horribly. Instead of actually being all hits, you can see that when I fetch, I do an address, maybe in fairness I should have written hit here, or at least maybe for the first time. But location, the data location where I'm fetched, so the instructions are coming from the thousands range and the data's in the 2000s range. When I access that first piece of data at word address 2048, what happens? It gets mapped to cache line 0, right? We're taking the address, the word address is mod 1024 because we have a 1024 location cache. So now what we discover is that some of the data and some of the instructions are colliding in the cache. In our direct map cache, we have 2 locations that are being mapped to the same cache line, and only one of them can live there. And if I'm in a loop, you can see what's going to happen is they're going to play bumper cars all the time. The data will push out the instruction will put out the data. So every time we look what we want, so we have a pattern that goes instruction, data, instruction, data, instruction, data, instruction, data. Every time I'm doing this, unfortunately, I'm kicking out the stupid, I'm kicking out the guy I'm going to want next. Okay, so this is what's called a collision problem. The addresses are colliding, in other words, they're mapping to the same cache line, and we're not finding anything in the cache. Now, if you want to amuse yourself, you can Google around and you can actually find programs that have been designed to break the Intel caches. In other words, they're designed to produce nothing but collisions in your caches. And your fantastic 2 gigahertz machine that you're so proud of actually turns into a couple hundred kilohertz machine because the caches are no longer working. Right? They're actually, now it turns out, as we'll see, Intel, like we're going to describe, actually has a more sophisticated cache architecture other than direct mapping. But if you break the cache, if there's some access pattern that causes the cache to perform poorly, your machine suddenly turns into a very, very, very slow machine. It's like going back in time 3 decades, in terms of performance. So it's quite remarkable. So you Google around, run one at home, and sort of go, my God, I didn't know anything that this simple could run this slowly on a modern machine. But now you know why. Okay, so here's our 2 choices. We have fully associative versus direct mapped as sort of a listing of comparisons. Speaking of comparisons, the number of comparators differs. So this search is very highly parallel in the fully associative system. This search only looks in one place. The replacement strategy, in other words, what to throw away, well, every time we bring something into a fully associative cache that can live anywhere, we have to pick where it should live. And so we throw away the least recently used item. In a direct map cache, there is no replacement strategy, right? Because it can only live in one location. For a particular address, I can perform the same mapping that the cache will perform and so identify the cache line it will live in. And so given a choice of, where's this going to, address 37, where's it going to go in the cache, it's only going to go in one place. So that's the location that will be replaced. Okay. So the real problems is is highly expensive but very effective in terms of implementing the functionality of a cache. Much more efficient from in terms of hardware and cost and power and speed even. Is the direct map cache, but it has the problem of contention. So what are we going to do? Was that a question or a almost question or metastable question? Okay.